Welcome back. We are on a roll, people. We are on section 4.4, a closer look at testing. And we're going to start with a little review. So it says, what is the p-value? When we talk about p-value, it says A, choice, the probability that null hypothesis of HO is true. Remember, the p-value is measuring statistical evidence moving away from the null hypothesis. So when we talk about a p-value, it has nothing to do with H of O being true as far as the probability goes. Okay, probability, H of O is always true. B, the probability that the alternative hypothesis is of H of A is true. Well, we don't talk H of A true. We talk about H of O true, and then we talk about probability. C, the probability of seeing data as extreme, there's a key word, as extreme as the sample when H of O is true. We have a winner, Johnny. Okay. Letter D doesn't even make sense to you right now, but it will pretty soon. And second question, the p-value of a hypothesis test is 0.02. Using an alpha level of 0.05. So what would you do if you had a p-value of 0.02 and you were comparing that to an alpha level of 0.05? Well, first of all, that says that the p-value is smaller than the alpha value. 0.02 is clearly less than 0.05. Okay, well then we would reject H of O. If the p-value is less than the alpha value, we have evidence to suggest that we should reject H of O. So, does the choice of mate improve offspring fitness? Okay, so somehow I lost my marker here. Let me see what happens here if I shoot this ahead. There we go. One study says that 6,067 of the 10,000 mate choices of Lauri survived, and 5,976 of the 10,000 of no mate choice Lauri survived. Okay, so we have a little bit of data here we produce. So first of all, we have two statistics there. And those two statistics can be put together in a proportion to take C, choice, which 6,067 divided by 10,000 is 0.607, and no choice proportion, which is 5,976 divided by 10,000, which creates 0.598. So our statistic is actually 0.09. This is our measurable statistic when we take proportion of choice and subtract proportion of no choice. If we calculate that using Stecky, and we'll do a little bit more of that today, but we did that the other day, we would get a p-value of 0.102. And it would look like this right here. Remember that the statistic always goes at the bottom, and this is 0.009, and the associated p-value is in the chart, which is the area of the data points which are as extreme as the statistic given. So there is actually there's a little more than 10% of the data that is as extreme as this value is. So if we were looking at these on a scale, we would start comparing this to an alpha level that is given for a test. So the question is, two studies investigated the same topic. One study found the significance results to be a p-value which was less than 0.01. That's a really small alpha level. That's a 1% alpha level. From a previous slide, the 0.009, which was 0.01. Okay, so in that previous slide that we just saw, we produced, and I'll go backwards to it so we can see it. Oops, hold on. Sorry. Let me go back here. We had that 0.10 alpha level. Okay, so this is a statistical test. This was done, and we got a p-value of 102. We did not reject the null hypothesis. When we look at this other test, they tested, and they got a significance value. It was 0.01. Those are dramatically different. It says one study found it to be 0.01 and one found it to be 0.102. Okay, well, how come there's a difference here? How come there are what we'll refer to as conflicting results? Okay, well, that's part of our topic today. Why can we have the same data being pulled and get two massively different results? All right, well, we have these references we have to talk about, and there are errors that can happen. In mathematics, we have errors that happen when we talk about testing. And we have two different things in our table here. One, we have what is really the truth, and we have what is the decision we are making. So as we walk through these, we have a couple of issues. So first of all, let's talk about the truth. The truth is H of O is false. So the null hypothesis is false, and we reject H of O. Okay, so if we decided to reject H of O, and the truth is H of O was wrong, then we made a good choice. A happy face there. There's also another happy face that could happen here. The other happy face that could happen is H of O was actually true. Okay, so the center was the center. Nobody was lying about that, and the data says it's true, and we did not reject it. We accepted it. Okay, so we failed to reject H of O, and we're happy about that. So we made good decisions. Now, there's two bad decisions here. First bad decision is called a type 1 error. A type 1 error says that H of O was true, but we rejected it. We have data that told us to reject H of O, but when in fact, if you go back and find the truth is H of O was actually true. We got rid of a true statement. That's an error. There's a second type of not happy face. It's called a type 2 error. So in this particular thing, the truth is that H of O is false. We should be rejecting it, but we failed to reject it based on the data. We have some name to type 1 and type 2 are the naming of this, and we go a little deeper into type 1 and type 2. It says a type 1 error is failure to reject a true null. Some people call this a false positive. A type 1 fail to reject a true null. Or excuse me, we reject a true null. And when we do this type 1 erroring, we make this false positive mistake, if you will. Go to my second, a type 2 error. A type 2 error is the failure in not rejecting. Okay? In a type 2 error, we didn't reject a null that was wrong. We like to call this sometimes a false negative. We're going to lead into these, but these are the two main things that happen here. Okay? These are the two main things that will take place. Analogy to law. So let's put this into an analogy law. So a person is innocent until proven guilty. So I have this person. They are definitely innocent. If I look at that in statements of H of O and H of A, H of O is innocent. Nothing's going on. H of A, you're guilty. This is what I'm seeking evidence for, if you will. So as I continue to go through, okay, well, how can I analyze this? So the evidence must be beyond a shadow of a doubt. Okay, so the evidence is what I am seeking a value of. It's a p-value. My evidence is my p-value from the data. Shadow of a doubt, that's the significance level. That's the alpha. So let's say that I do something bad. Let's say that I make a misverdict. Okay, so what can happen? We can convict an innocent man, right? So if we convict an innocent man, we are rejecting H of O. We're rejecting that nothing is going on when in fact H of O was true. That is a type 1 error. We're convicting an innocent person, and when we convict an innocent person, that's a type 1 error. We rejected H of O when in fact nothing was going on with H of O. Now let's say we release a guilty man. If we release a guilty man, we rejected or we failed to reject H of O, and H of O was actually true. It should have been rejected. We failed to get rid of that statement. And when we do that, that's our type 2 error. We'll break it down a little farther into statistical data and say that, you know what? When we're rejecting H of O, when the null hypothesis is really true, okay, this is going to be our type 1 error. We're rejecting H of O when the null hypothesis is really true is our type 1 error. That's what happened in study number 1. When we had a 0.01 and we rejected H of O because of that 0.01, but in fact, H of O was actually true. We shouldn't have got a 0.01. We had some data that suggested we do that, though. A type 2, a second study. The second study got a 0.102. On a 0.102, you would not reject. And a type 2 error is not rejecting H of O because we had a 102, but the null hypothesis was really false. We should have rejected it. We should have made it go away. And option number 3, no errors were made and different experiment settings yield different results. These 3 things can happen. So in this mate choice offspring fitness that we're referring back and forth to, the first thing that could be true, or the first thing that could have happened, is somebody made a type 1 error. And in a type 1 error, they rejected H of O, but the null hypothesis was really true. Well, maybe there was a type 2 error, right? Well, in a type 2 error, the second team maybe didn't reject H of O when they should have, and the null hypothesis was really false. In option 3, no errors were made, and as we will see in this course, it's possible to get different data from different tests. Seems very confounding, right? Type 1 error. Type 1 error, if you think about it, is the incorrect rejection of a true null hypothesis. That is really the statement that I like best. It's the incorrect rejection. So if you incorrectly get rid of a null, meaning it was true, you made a type 1 error. It goes on to say that this is to conclude that a supposed effector relationship exists when in fact it does not. Conclude means that we were different when in reality there was no difference. We chose to say, this thing I am measuring is different, but actually there was no difference. A result that indicates that a given condition is present when it is actually not present. We are believing a lie, if you will. Okay? Believing a lie. I like my students to agree with that statement when they're looking at a type 1 error. Example, a test shows that a patient to have a disease when in fact they do not have the disease. That would be a bad thing to report to somebody that they have stage 4 cancer. And guess what? I made a type 1 error. You don't have it. The stats came back wrong. A fire alarm going off or on, indicating you have a fire, but there's no fire. That's a type 1 error. You're believing a lie. An experiment indicates that a medical treatment has a cure for disease, but in fact it doesn't do anything. Again, type 1 error. A type 2 error. It's the failure to reject. You fail to reject something that should have been rejected. You missed your diagnosis. We conclude that the means are not different, but actually they are. The actual hit was disregarded by the test and seen as a miss. We call this a miss often. We fail to believe a truth. An example, a blood test fails to detect a disease that it was designed to detect in a patient who really has the disease. A fire breaking out and the fire alarm does not ring. A clinical trial of a medical treatment which fails to show that the treatment works when it really does. So we do the measurements on this stuff. We say, hey, stop taking the medicine. It doesn't work. But actually, it was working. These are type 2 errors. In the situation below, describe what it means to make a type 1 and a type 2 error. We are testing to see if a well-known company is lying in its advertising. If there is evidence that the company is lying, the Federal Trade Commission will file a lawsuit against the company. A type 1 error. So remember, I believe a lie. You sue the company for lying in its advertising. That's not a type 1 error. We let the company off the hook. Okay, well, that's not a type 1 because remember, we let them off the hook when they were doing that. All well-known companies are lying. Okay, again. D, let the company off the hook when they are actually lying in their advertising. All well-known companies are lying and not are not lying on their advertising, and sue the company when they are not lying. Now remember, we're trying to choose which one does what. So when we talk about suing the company when they are not lying, remember that this is a type, when we talk about a type 1 error, a type 1 error is the incorrect rejection of a true null. Okay? So the true null is that they are not lying, and we sue that company for that fact. A type 2 would be for us to do what it said in letter F. They are not lying. That's the true null. But we act on that and we believe in a lie. Continue the situation. Now let's talk about the same exact thing, but it's a type 2 error. Type 2 error. So now, remember, in a type 2 error, we're looking for the failure to reject the null hypothesis. We miss. Okay, so we need to look for the one that says, I'm going to let them go because I don't believe they did anything wrong, but they're a bunch of crooks. Well, I think letter D is our answer here. They were lying. That was actually happening, and we didn't believe it, and we failed to reject. We failed to act on something that was actually taking place. We missed a type 2 error. Probability of a type 1 error. Okay, well, what's the probability of a type 1 error taking place? Distribution of the statistic of H of O is true. So when we talk about things that are things that happen, so remember, in a type 1 error, I believe in a lie. Okay, well, what would make me reject the null hypothesis? Everything in here would make me reject. These are the occurrences which take place which cause rejection. So if the null hypothesis were true, 5% of the statistics will be in the most extreme. There are 5% of the data points floating around out there on the left-hand side. So what does that mean for me? It means 5% of those statistics will give me a p-value of less than 0.05. Well, what will I do with those values? I would actually reject them with those values. So 5% of these stats will lead to me rejecting H of O at an alpha level of 0.05. So what does that mean? It means I have a 5% chance of a type 1 error. If the alpha level is 5% or 0.05, then 5% of the data will cause me to make an error. Seems crazy, right? Well, that's why we'll talk about changing that alpha level and making it harder for this to happen. Here's another one. Here's a type 1 error again. Same deal. And you can see that we have a p-value of 0.01 right here. That means 1% of the data is as extreme as the statistic that's being measured. And we're talking right now about a type 1 error. So we're talking about me getting those data points. If the null hypothesis is true, 1% of the stats are in the most extreme. Again, 1% of the stats will give p-values, which I will designate as being less than the significance level. 1% of the stats will lead to me rejecting, so I have a 1% chance of a type error. I'd certainly rather have a 1% chance than have a 5% chance, depending on what I'm measuring, though. As we're going to see, there are times when you'll prefer to have a type 1 probability compared to a type 2 probability error. It says the probability of making a type 1 error, rejecting the true null, is the significance level alpha. Need to underline that. The significance level alpha is the probability that you will make a type 1 error. I don't know how that happened, but it's really cool looking. Because the chance of a type 1 error is alpha, alpha of all tests with true null hypotheses will yield significant results just by chance. Meaning, whatever the alpha level is, that's going to be your probability of making an error. It says if 100 tests are done with an alpha level of 5% and nothing is really going on, 5% of them will yield significant results just by chance. This is known as the problem of multiple testing. If we continue to test and continue to test and continue to test, and I reach a certain number and I have an alpha level of 5%, I'm going to find 5% of the data that says you have found something significant. And it's very possible that nothing was going on and the null was true. In multiple testing, consider a topic that is being investigated by research teams all over the world. Using a 5% alpha level, 5% of the teams are going to find something significant even if the null hypothesis is true. We could equate this to today, what all of us are experiencing right now through social distancing. We could look at all the testing that's being done, and on a 5% significance level, 5% of those tests will come back as being significant, and 5% of those tests have the ability of being wrong under a type 1 error, meaning you said something was happening or you said somebody had this particular virus and you did not have it. Consider a research team doing many hypothesis tests. The more you do, the quicker you're going to get to something being wrong. It's just the law of averages, and we cannot get around that law of averages. It's always going to take place. So we need to adjust our significance level in order to meet the needs of the test. So here we talk about actually doing that. It says for each situation, let's describe and indicate whether it makes more sense to use a significance level of 0.1, which means 10% of the things could be wrong, or a smaller one where 1% of them could be wrong. So we're moving out the measurement of error. I'm testing a new drug with potentially dangerous side effects to see if it's significantly better than a drug that is currently in use. If it is found to be more effective, it will be prescribed to millions of people. All right. So first of all, we have potentially dangerous conditions. We're going to give it to millions of people. We don't want to be wrong. We don't want to use an alpha level of 10%. We want to use an alpha level of 1% or even smaller than 1%, but those are the two we're given. We want to minimize the number of errors of type 1. Using a sample of 10 games to see if your average score on Wii Bowling is significantly more than your friend's average. I don't think that anybody's going to get hurt because you have a higher average than somebody else on Wii Bowling, but some people are really competitive, so it could happen. I'm sure my wife could put the whooping on me if I beat her in bowling or something. So I don't want to miss all of the things that could happen, so I want to open up my significance level. I want to increase that significance level to more of a 0.1. Nobody's going to get hurt on a 10% significance level. Lots of people will get hurt if I use the 10% significance level and I miss something on question 17. It says a company advertises that the milled flaxseed contains on average at least 38, at least, I got to underline that, at least 3,800 milligrams of omega-3 fatty acid per tablespoon. In each case below, which of the standard significance levels, so we have a choice of 1%, 5%, 10%, make the most sense for the situation? So letter A says the company plans to conduct a test to double check to claim. The company is eager to find evidence that the average amount per tablespoon is greater than 3,800 and is not really worried about making a mistake. Nobody's going to get hurt because I made a mistake. The test is internal in the company and there are unlikely to be any real consequences either way. Okay, I'm going to open that up for an alpha level of 10%. Nobody's going to get hurt. I'm just running the test in the company. No consequences either way. Let's see what I think. The customer organization plans to conduct a test to see if there's evidence against the claim containing 3,800 milligrams. If the organization finds evidence that the advertising claim is false, it will file a lawsuit. Okay, now we have actions. The organization wants to be very sure, and here's the word, the evidence is strong. All right, well, if the evidence is strong, I'm going all the way down to the 1% alpha level. And I'll write this one as a percentage, or 0.01. It says Mate Choice and Offspring Fitness said the experiment was actually comprised of 50 smaller experiments. So we're going to actually see the data from this calculation of 0.1 and 0.01. And if we look at this, these are all the different data values that happened. These are the 50 different tests and the 50 different p-values. Look at the extremities. This one right here had a p-value of 1.0, meaning every single data value was under the curve. But over here, somebody ran the test and got a 0.0001. That is a serious conflict of interest. Well, if you run a test enough times, you will find significance. Because remember, the alpha level will contain that percentile of type 1 errors. Question here. Here's a question somewhere. There we go. What if we just reported and run the yield of the p-value of 0.0001? The question is that ethical? Well, if we look at the other data, for instance, 0.95, 0.98, 0.99, 0.88, these things are extremely far away from 0.01. There are not many values here that are less than 0.05. I can only find a couple, maybe 2 or 3. So would that be ethical? Absolutely, positively not. Publication bias. And this reporting of data that you find to be extreme in your benefit is referred to as publication bias. It refers to the fact that we usually only get the significant results published. I could conduct a test 1,000 times, and if nothing really important happens, nobody talks about me. But the minute I push out there that, hey, I found something with a 0.001 significance level, now somebody's going to talk about that. That's bias. The one study that turns out significant level gets published, and no one knows about all the insignificant results, also known as the file drawer problem we talk about sometimes. This, combined with the problem of multiple testing, can yield very misleading results. As you study statistics more, if you look at statistics more, you'll be amazed at the amount of information you take in from the public and what actually is misleading and what is bent on showing you what it wants. So let's talk a little bit more about multiple testing and publication bias. So as we look at this, the alpha level becomes incredibly important. The alpha of all tests with true null hypotheses will yield significant results just by chance. The one that happens to be significant is generally the one that gets published. It says this should scare you, especially in today's day and age right now. If we are conducting many hypothesis tests to test a claim, assuming H of O is true, approximately how many tests will be incorrect at their significance? Well, if we have 40 tests and we're using a significance level of 10%, then 40 of those tests at 10% means that of just that test, 4 of them are going to find significance. The law of averages says 4 times I'm going to get something significant. And 40 tests is not a lot of tests to conduct. So what can you do? First of all, errors of type 1 and type 2 are possible. You have to know that. Multiple testing and publication bias are a huge problem, reporting only the things which are significant. Is it hopeless? Well, no, not really. You can recognize and be skeptical when you see a claim. Don't believe just one test. Look at all of the tests. And look for replication. That's the key, in that results can be replicated by other institutions, other testing facilities. Replication is that I put it into another setting with another researcher, and it is also significant when it is being double checked, if you will. Studies that have been replicated in similar conclusions gain credibility. So when you can have somebody back up what you have done, then that's a big deal. Studies that have been replicated with different conclusions, they lose credibility pretty quickly. And replication helps guard against type 1 errors and helps with generalizability. Let's talk a little bit more about a type 2. It says we can reduce the probability of making a type 2 error. Now remember, a type 2 error was not rejecting a false null. How can we do this? We can increase the significance level for the value. We can also increase the sample size. Excuse me. Okay, on the last one, on a type 1 error, we decreased the significance level. We went from an alpha level of 5% to an alpha level of 1% in order to squeeze out all of those misses. In a type 2, remember, a type 2 is we failed to reject. So we didn't have significant evidence. So now we're going to broaden that range and say, you know what, we're going to let that number in, because now we're going to make that thing statistically significant. So an alpha level, if we reject H of O, we could be making a type 1 error. Chance of a type 1 error is equal to my alpha level. But if I don't reject H of O, I could be making a type 2 error if H of A was truly true. And this is related to the chance of making a type 2 error. Now, how do I decide between what's more important, a type 1 or a type 2 error? Well, first of all, we decrease the alpha if a type 1 error is very bad. If I make an error based on rejecting H of O, and I'm making a type 1 error, and that's bad, I am going to decrease the alpha level. I'm going to make it smaller. But if by me failing to reject, I did not reject H of O, and that was bad, and I'm making a type 2 error, I'm going to increase the alpha level. This screen right here is a really important screen for understanding the adjustment of the significance level. On a type 1, you take it down. On a type 2, you take it up if it's causing something which is very bad in the scenario you're dealing with. We'll make that decision here in a second. Larger sample sizes also make it easier to reject a null. So if we have a p-value of 0.05, nothing going on, and we're looking to measure greater than 0.05, and we get a p-hat of 0.06. So first of all, I get a p-value under a random distribution of 0.359, and notice there were n values of 10. 10 things were measured. I'm going to rerun that exact same test, but when I rerun that exact same test, now I'm going to put 100 n's in. Look at what happened to the p-values. Simply increasing n number of things increased the p-value to a significant level. You never would have rejected with 0.359, but you definitely would reject with 0.02. You would have rejected a 5% alpha. Simply increasing the number of n values increases that significance of that data statistic. So I open up that error possibility by increasing n and getting rid of these returns, these things that I should not have rejected. So if you increase n to decrease the chance of a type 2 error. Let's get that through and make sure we're thinking right about that. I increased n. Look what happened. When I increased n, my data went outward, and the data statistic, it stayed exactly the same. It was a 0.6 and it was a 0.6. Nothing changed the data point. But over here, I rejected. Over here, I did not reject. Kind of a bad not, sorry. I did not reject the p-value on the first with a small n size. But when I increased that n value, I did reject. Remember the type 2 failure to reject. Effects of sample size. So it says the larger sample size makes it easier to reject. With small sample size, even large differences or effects may not be significant. It's hard to get those measurements when you're talking about things which didn't have a lot of data behind them, is really what happens when the sample sizes are small. With large sample sizes, even very small, different ones, the effect can be significant. It says use StatKey to find the p-value and indicate whether the result is significant at 5%, which is the sample size provides the strongest evidence for. Okay, so let me get some data up here. So we're looking at, first of all, 0.5% at nothing going on, or 0.5, nothing going on, and we're measuring a stat of 0.58. We're going to do it with two different sample sizes. The first sample size is 50, right there, and the second sample size is 500, right there. So I'm going to go to the computer. I'm going to switch over so we can go to StatKey, and we're going to watch what happens. Give me StatKey. Here we go. I got to jump all over the place. Sorry, give me a chance. There we go. And let's go to StatKey. All right, so let's go take a look at a single proportion. Let's edit the data, and let's put in 29 out of 50. Oops. Okay, so you can see that my sample size is 50. Okay, n is 50. Right here, sample size 50. And I'm going to run 1,000. Oops, sorry. I'm going to run 1,000. And in that 1,000, I'm going to go down to I'm going to do a right-sided test. And I'm going to check at 0.58. That was my statistic, 0.58. And I'm going to hit OK. Look at my p-value. 166, okay? Nobody's rejecting 166, all those data. This is nothing significant at all. Now, I'm not going to change anything. I'm going to keep the 0.58, but what I'm going to do is I'm going to change n. I'm going to go in and I'm going to edit the data. I'm going to make it 290 out of 500. I just increased the sample size to 500 instead of 50. I'm going to rerun the 1,000. I'm going to go down and I'm going to do the right side tail, and I'm going to do this at 0.58 one more time, and look at what happened to the p-value. It got extremely small. Matter of fact, it's small enough to reject at 1%. Simply changing the number of n values gave me a massively different give me a massively different result from no changes at all in data. I still had a 0.58. There was no difference in that. The only thing that happened here was that I used a 500 N value instead of a 50 N value. Data is extremely affected by sample sizing, and sample sizing can lead to reduction of type 2 errors. I'm going to let you do this one. This is question 9 for Wiley. It's going to be the same. I'm going to give you my answers of what I got real quick, and you'll be able to check yours. So when I ran the first sample, I got 292. You should be approximately, but not the same. On the second one, when I changed the sample size, I went all the way down to 0.009. Are the results significant at a 5% level? Okay, so when I look at the 5% level in both of these, well then, yeah, absolutely, yes. Yes. Why is it significant? Because 0.009 is less than 0.05. Remember, the p-value, is it smaller? Which one provides stronger evidence against H of A? Well, B obviously provides stronger evidence. And I want you to run that and go through that. And here's the difference. Look, N changed from 30 to 300. You made the N value 10 times bigger than it used to be. Let's talk statistics versus practicality. Statistical significance is not the same as practical significance. Good statement right there. A statistically significant result is not always practical significance, especially with large sample sizes. Significance is not the same thing. This would be, suppose a weight loss program recruits 10,000 people for a randomized experiment. A difference in average weight loss of only 0.5 pounds could be found to be statistically significant. It could be. But suppose that the experiment lasted for a year. Is a loss of a half of a pound practically significant? Well, no. I mean, statistically and practically are not the same thing. If you go to somebody and say, hey, statistically, you could lose a half of a pound, that might be a big deal to them. But if you say in practicality, it's going to take over a year to do that, probably not a lot of people are going to be swayed. To summarize, conclusions based off p-values are not perfect. We cannot assume perfection out of this because there's error. Type 1 and type 2 errors can happen. Study those type 1 and type 2 errors, folks. Alpha levels of all tests will be significant just by chance, and often only the significant results get published. Remember, that's our bias. Replication, that's important. And larger sample sizes make it easier to get significant results. If you want to get significance in your tests, get some big N numbers and you'll get something happening. For more details, you can check out this particular link. And have a great day. That's section 4.4, and I'll see you in section 4.5.